Chemistry is awesome.
Right, Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So welcome back to my channel. Right, class, today we are going to have a look at still we are still in topic 1.3 stoichiometry, but this time around we are going to have a look at how to perform stoichiometric calculations using mole concept. Okay, so in the previous lesson or in the previous video we have already have a look at how to write and also how to balance chemical equations using two different methods. Okay, so what were those two methods? If you can still remember, the first method was through inspection method. Okay, the one with that we are balancing the chemical equation using using inspection method. And the second method, we are using the ion electron method, and that method is especially for balancing redox equation, whether it was in acidic or in basic medium. Okay, maybe some of you might wondering why must we write a balanced chemical equation. Okay, the reason why the equation must be balanced because of this. Right, class, let's say we have a balanced chemical equation. So let's say if we know the moles of one substance in the balance equation, of course, okay, the balance equation tells us moles of all of the other substances in the same reaction. So that's why balanced chemical equation is very important, because if you balance it wrong, okay, we are going to have problems, especially when it comes to problem solving that requires us to calculate the moles or anything that is related to the equation, to the balance equation. Okay, for example, I'm going to use this reaction or this equation. So what do we have here? We have propane. Okay, propane is combusted in oxygen gas, and what do we get? Actually, are carbon dioxide gas and water. Okay, so from this equation, we know that 1 mole of propane reacts with 5 mole of oxygen gas to produce 3 moles of carbon dioxide gas and 4 moles of water. Right. So how can we read this equation? Okay, so it's like this. So we can say that 1 mole of propane reacts with or needs 5 mole of oxygen. Since oxygen is the reactant here, okay, and this oxygen reacts with propane, so in the form of a stoichiometrical relationship, we can write like this, or it is also can be written as 1 mole of propane produces 3 moles of carbon dioxide, or 1 mole of propane produces 4 moles of water. See the relationship here, okay, between the products and the reactants. Or if we don't want to use propane, we can also use the oxygen gas here. So same as propane. So since oxygen also is the product, is the reactant, okay, so therefore 5 mole of oxygen produce 3 moles of carbon dioxide, or 5 mole of oxygen produce 4 moles of water. See the relationship still, okay, between reactant and products. Okay, or if we look at the products itself, okay, say for example 3 moles of carbon dioxide gas are formed from 1 mole of propane, or 3 moles of carbon dioxide gas are formed from 5 moles of oxygen. And lastly, we can also use water, okay, to show the stoichiometrical relationship. For example, 4 moles of water are formed from 1 mole of propane, or 4 moles of water are formed from 5 moles of oxygen. See, so these are what we call as stoichiometrical relationship between the reactants and reactants, reactants and products, and products and products. Okay, so next I'm going to show to you a few examples of problems. Right, so now let's start with the first example, example 1. Okay, so what do we have here? We have methanol. Okay, methanol, which is an alcohol, burns in air according to the given equation. So we have 2 moles of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 4 moles of water. Let's say the methanol used in this reaction is 209 grams, okay, or 209 grams of this methanol is combusted, completely combusted. What mass of the water produced in this reaction? Alright, so now let's look at the solution, or the answer to this example. Okay, so firstly, what we need to do is we need to determine how many moles of methanol combusted in this reaction. If we look back at the previous lesson, okay, 1.2 mole concept, you have already learned on moles, okay, and then the molarity. Okay, so we are going to use that in this solution. Okay, so since we want to determine the mole of methanol, so mole of methanol equals to mass of methanol divided by molar mass of methanol. Okay, so the mass of methanol is already given in the question, which is 209 grams divided by 32 grams per mole, and we are going to get 6.5313 mole of methanol. Okay, so this is the mole of methanol combusted in the reaction, right? So from the equation, or from the balance equation, okay, given that if we have 2 moles of methanol, okay, combusted, we are going to get 2 moles of carbon dioxide and 4 moles of water, and this reaction requires 3 moles of oxygen gas. Okay, so since we want to determine the mass of water, so we are going to look at the relationship, the stoichiometrical relationship between methanol and water. So from the equation, 2 moles of methanol produce 4 moles of water, but we only have 6.531 mole of methanol. Okay, more than 2 moles. Okay, so if 2 moles produce 4 moles of water, so of course if we have 6.531 mole of methanol combusted, of course this reaction will produce more than 4 moles of water. And how many moles of water actually produced in the reaction? If you calculate this you're going to get 13.063 moles of water. Okay, so why 13.063? Because 6.531 mole of methanol, okay, combusted. Right, but the question asks you to determine its mass, the mass of water produced. So since we have already determined the mole of water produced in the reaction, okay, so from mass of water, we know that mass of water, okay, equals to moles of water multiplied by or times molar mass of water. So mole of water 13.063 mole times 18 grams per mole, okay, which is the molar mass of water, and you are going to get 235.1 grams of water. So this is the answer for this question. Okay, example 2. A popular candy bar, okay, and don't ask me, okay, what candy bar is this, okay, it remains unknown. Right, so contains 21.1 grams of sucrose. So if you want to know what is sucrose, normally in the form sucrose can be found, okay, mostly can be found in cane sugar, okay, cane sugar, with the molecular formula C12H22O11. Right, so when this candy bar is eaten, so what happened was the sucrose in the sugar, in the cane sugar, is metabolized according to the given equation here. And do keep in mind, this given equation is unbalanced. It's unbalanced, okay? And the question is, find the mass of oxygen consumed and the masses of carbon dioxide and water produced by this reaction. Right, so what should we do first? Okay, so we are going to calculate how many moles of sucrose reacted in the reaction. So same as the previous example just now, so to determine the mole, we are going to use mass of sucrose divided by molar mass of sucrose. Okay, so given in the question, the mass of sucrose is 21.1 grams divided by 342.30 grams per mole. Okay, so if you are wondering from where actually we get this value, actually this value you need to calculate this value by yourself. If you forgot the values, no worries, you can just refer to the table of relative atomic mass in your tutorial book. At the back side of your tutorial book, you will find it there. Okay, so how to calculate this molar mass of sucrose. Okay, and then we are going to get 0.06164 moles of sucrose. So this is the number of moles of sucrose reacted. Alright, right, then we are going to look back at the given equation, but in the question, the given equation actually is not balanced yet. And then what we need to do, actually we need to balance the equation, and if you balance the equation correctly, so this is how it looks like. So this is the balance equation, okay. So from the balance equation, if we read the equation, see, 1 mole of sucrose needs 12 moles of oxygen gas. So this is the stoichiometrical relationship between the two reactants in this reaction. Okay, but we don't have 1 mole of sucrose. What we have is 0.06164 moles of sucrose. So therefore it needs how many moles of oxygen? It needs 0.7397 moles of oxygen gas. So this is the amount of oxygen gas required if we have 0.06164 moles of sucrose. Okay, since we want to find its mass or the mass of oxygen, okay, so we are going to use this formula. So mole of oxygen, okay, multiply by molar mass of oxygen, okay, and you substitute the values, okay, right? So mole of oxygen 0.7397 mole, and times 32 grams per mole. This is actually the molar mass of oxygen, because oxygen atom, the molar mass is 16. So oxygen molecule is O2, so 16 times 2, so we are going to get 32 grams per mole. You solve for this, you're going to get this answer, 23.7 grams of oxygen. So this is the mass, or this is the amount of oxygen required or needed in the reaction. Alright, let's move on to the next part of this question. Okay, so from the balance equation also, we knew that 1 mole of sucrose produces 12 moles of carbon dioxide. So this is also the stoichiometrical relationship between reactant and product. For example, the reactant is sucrose and the product is carbon dioxide. Okay, since we only have 0.06164 moles of sucrose, so therefore it will produce just 0.7397 moles of carbon dioxide. Okay, and we are going to do the same thing as what we did with oxygen gas, since we want to determine the masses, the mass of carbon dioxide. So therefore moles of carbon dioxide times molar mass of carbon dioxide. So we are going to get 0.7397 moles of carbon dioxide times with 44.01 grams per mole, which is the molar mass of carbon dioxide, and we are going to get 32.6 grams of carbon dioxide. So this is the mass of carbon dioxide produced in the reaction. Okay, so we are done with this question. So now let's move on to the next. Okay, also from the balance equation, okay, from the same balance equation, right now we are going to determine the mass of water. Okay, the mass of water produced in this reaction, the same reaction. Okay, 1 mole of sucrose from the equation, from balance equation. So 1 mole of sucrose produces 11 moles of water. Since we only have 0.06164 moles of sucrose, so therefore we are going to get how many moles of water? So you calculate this, we are going to get only 0.6780 moles of water. Okay, so once again, for the third time, okay, we are going to determine the mass of water. Just now we have determined the mass of oxygen and then the mass of carbon dioxide, and right now we are going to determine the mass of water produced in this reaction. So still we are going to use the same formula, mole times molar mass. Okay, so in this case, so mole of water 0.6780 times with molar mass of water 18.02 grams per mole, and we are going to get 12.2 grams of water. So this is the mass of water produced in this reaction. Okay, right, now let's move on to the third example and to the next question. Okay, so in this question, question number 3 or example 3, the question is how many grams of phosphorus react with 35.5 liters of oxygen gas at STP to form tetraphosphorus decaoxide P4O10, and the equation is given here. Okay, right. So first of all, we need to determine the mole of oxygen gas. Okay, so in the question, it is stated in the question, this reaction occurred at STP. So you guys, do you guys know what is STP? What is STP? So STP actually is standard temperature and pressure. So what is the conditions for this STP? So the temperature is 0 degrees Celsius and the pressure is 1 atm. So these two conditions, this is what we call as STP. Okay, standard temperature and pressure. So at STP, if we have 1 mole of gas, any gas, 1 mole of any gas, so this gas will occupy the volume of 22.4 liters. Okay, remember at STP, 1 mole of any gas occupies 22.4 liters of volume. Right. So now let's get back to this question. So right now we know that since this reaction occurred at STP, okay, so 1 mole of oxygen gas occupies 22.4 liters. But in this question, we have at STP 35.5 liters of oxygen gas. So therefore, how many moles of oxygen gas actually, okay, did we have in this reaction? So to calculate this, so 35.5 liters times 1 mole of oxygen gas, 22.4 liters. Okay, divide by 22.4 liters. So we are going to get 1.5848 moles of oxygen. So this is the mole of oxygen gas, right? Okay, so from the equation, from the equation, so if you look at this equation, 5 mole of oxygen produce 1 mole of phosphorus decaoxide, okay, P4O10. Or we can write it down as 5 mole of oxygen need 1 mole of phosphorus. Okay, so 5 mole of oxygen need 1 mole of phosphorus. But in this reaction at STP, from what we have calculated just now, okay, we only have 1.5848 moles of oxygen. So therefore, okay, 1.5848 moles of oxygen need how many moles of phosphorus? So we are going to get 0.317 mole of phosphorus. Okay, so this is the mole of phosphorus reacted with oxygen gas in this reaction at STP. Okay, and since we want to determine the mass of phosphorus, okay, once again, okay, mole times molar mass. So mole of phosphorus times with molar mass of phosphorus, okay, 0.317 mole times 123.88 grams per mole, which is the molar mass of phosphorus. So we are going to get 39.3 grams of phosphorus. Okay, right. Example 4. In this fourth example, this question wants you to find the volume in liters and also in milliliters of a 0.505 molar of sodium hydroxide solution required to react with 40 milliliters of 0.505 mole of sulfuric acid solution according to the given equation. Okay, so this is the given equation. We have 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide to produce 1 mole of sodium sulfate and 2 moles of water. Okay, so firstly what we need to do is we need to determine, or we need to find, how many moles of sulfuric acid react in this reaction. Okay, since we were given the molarity of sulfuric acid and also we were given the volume of sulfuric acid solution used in the reaction, so from here we can determine the moles of sulfuric acid, molarity times volume, mv. Okay, mv. So this is the molarity or the concentration of sulfuric acid solution, and this is the volume, so molarity times volume. So we are going to get 0.0202 moles of sulfuric acid. So this is the quantity, or this is the amount of mole of sulfuric acid used in this reaction. And then we are going to look back at the equation given. So from the equation, okay, 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. So therefore, if we have 0.0202 moles of sulfuric acid, so this quantity of sulfuric acid, okay, should react with how many moles of sodium hydroxide? We are going to get 0.0404 moles of sodium hydroxide, because the ratio is 1 to 2. 1 to 2. Okay, so this is the mole of sodium hydroxide reacted. Okay, if the mole of sulfuric acid is 0.0202 mole of sulfuric acid. Okay, next. So next is we want to determine the molarity of the solution. Okay, since molarity of the sodium hydroxide is already given, okay, and we have already determined the moles of sodium hydroxide from the previous stoichiometrical relationship just now, and using this equation we are going to calculate the volume of sodium hydroxide solution needed to react with the sulfuric acid. Okay, so volume of sodium hydroxide, so we just rearrange this equation. Okay, so the equation, since we want to determine the volume, okay, so volume of sodium hydroxide solution in liters equals to moles of sodium hydroxide divided by its molarity. So the mole is 0. I think there is a mistake here. It should be 0.0404. Okay, so divide by, hold on, let's look back at the, I think it should be, yes, it should be 0.0404. Okay, so there is an error here, so typo. Okay, it should be 0.0404 moles. Okay, sorry for the mistake. Okay, 0.0404, so you just make the correction. Okay, divide by 0.505 mole per liter. So this is the this is the concentration of sodium hydroxide solution given in the question. So we calculate these two. Okay, so we are going to get 0.08 liters. Okay, so this is the volume of sodium hydroxide solution, and since the question wants us to determine the volume in liters and also in milliliters, so that's why if we convert from 0.08 liters to milliliters, we are going to get 80 milliliters of sodium hydroxide solution. Okay. Right, example 5. Okay, so this time in this reaction, we have a different reaction, and this time we have silver nitrate and excess silver nitrate reacts with 110.5 ml of an aluminum chloride solution to give 0.215 grams of silver chloride. And the question is, what is the concentration in mole per liter of the aluminum chloride solution? And this is the equation given. So now let's look at the solution, or let's look at the answer, how to solve this problem. Okay, so firstly, we are going to start with the moles. Okay, we are going to calculate the mole of silver chloride. So mass of silver chloride divided by molar mass of silver chloride, and we are going to get 0.215 grams divided by 143.32 grams per mole. Okay, and this is the mole of silver chloride. 1.5 exponent negative 3, or 1.5 times 10 to the power of negative 3 mole of silver chloride. Okay, and then from the equation, so that's why balanced chemical equation is very important, because if you balance it wrong, so the stoichiometrical relationship would be wrong also. Okay, so that's why you need to balance them. If the equation is not balanced, we need to balance the equation first. Okay, or balance the equation correctly. Okay, or else we are going to have problems. Okay, right. So since the equation given here was already balanced, okay, alright, and then from this equation, let's look at the relationship between silver chloride and aluminum chloride. So from the equation, 3 moles of silver chloride, okay, which is the product, okay, produced from 1 mole of aluminum chloride. Okay, so therefore, if we have 1.5 exponent negative 3, or times 10 to the power negative 3 mole of silver chloride, so they are produced from how many moles of aluminum chloride? So you calculate this, you're going to have the answer should be 5 times 10 to the power of negative 4 mole of aluminum chloride. Okay, so this is the mole of aluminum chloride, okay, reacted in this reaction. If the mole of silver chloride produced is 1.5 times 10 to the power of negative 3 mole. Okay, next we want to determine the molarity, okay, of the of aluminum chloride. Okay, so molarity equals to moles of aluminum chloride divided by volume of aluminum chloride in liters, aluminum chloride solution in liters. Okay, so 5 times 10 to the power negative 4 mole divided by the volume, 0.1105 liters, and we are going to get the concentration of the aluminum chloride solution is 0.00452 mole per liter, or molar of aluminum chloride solution. Okay. Okay, so what is purity of samples? Right, so purity of samples is defined as the percentage by mass, or the mass percentage, or also we can use the mass composition, right, so of a specified substance in an impure sample. Okay, so I'll give you one example. So let's say we have a sample of sodium hydroxide. Okay, sodium hydroxide. So normally the sample that we are using, in some cases, the sample is not really 100% pure. Okay, and it might contains impurities, and that's why we need to determine actually, okay, how many or what is the percentage, what is the percentage of the pure substance in the sample. Okay, so to calculate this, we are going to use this formula. Okay, so purity of samples is equals to the mass of pure substance divided by mass of impure sample, or the total mass of the sample. Okay, and we multiply with 100. Okay, so by if we use this equation, we can simply calculate the purity of samples. Okay, so remember just now I have said that let's say we have an impure sodium hydroxide sample. Okay, so we want to know in that impure sample of sodium hydroxide, so how many percent actually from the total sample, or from the total mass of the impure sample, is the mass of or the percentage of pure sodium hydroxide. Okay, so let's say we have I'm going to use one example here. Okay, so let's say the mass of the impure sodium hydroxide is 50 grams. Okay, it's 50 grams. So now we want to calculate the purity of sodium hydroxide in the sample. Right, so how to calculate this? So based on the given equation here, okay, so mass of pure sodium hydroxide, so in this case let's just use this value. So let's say the mass of pure sodium hydroxide is 49.4 grams. Okay, so divide by 50 grams, which is the total mass of the impure sample of sodium hydroxide, right? And you multiply with 100, and we are going to get 98.8%. Okay, so what actually this 98.8% means to you? Okay, so how to read this percentage? Okay, so 98.8% here means the sample contains 98.8% of pure sodium hydroxide, while the remaining 1.2% is the percentage of what? Yes, percentage of
impurities.
Okay, right, so now let's look at a few examples, or a few exercises, so that you get a clear understanding on this purity of samples. Okay,
So what do we have here? Okay, see, we have an impure sample of solid sodium carbonate. And what happened was, this impure sample of solid sodium carbonate is allowed to react with 0.1755 molar of hydrochloric acid solution. And this is the equation of the reaction. Okay, right. So let's say we have 0.233 gram sample of sodium carbonate requires 17.85 milliliters of hydrochloric acid solution. What is the purity of the sodium carbonate?
okay, so to solve for this, so firstly what we need to do is, right, so we need to calculate how many moles of hydrochloric acid used in the reaction. Okay, so we are going to use this formula, molarity times volume. Since the molarity was given together with the volume of acid, okay, also given in the question, so we just simply substitute these two values into this equation. Okay, so 0.1755 molar times 0.01785 liters, and we are going to get, okay, 3.13 times 10 to the power of negative 3 mole of, and remember, this is the amount of HCl reacted with, reacted with sodium carbonate. Okay, so now let's get back to the equation. Okay, so now we are going to apply a stoichiometrical relationship here. Right, so let's look at the given equation. Okay, so from the equation, okay, 1 mole of sodium carbonate reacts with 2 moles of hydrochloric acid. Okay, or it can also be written as 2 moles of hydrochloric acid react with 1 mole of sodium carbonate. Okay, but we don't have hydrochloric acid, okay, in the quantity of 2 moles. So how many moles of hydrochloric acid actually reacted in the reaction? This is the amount of hydrochloric acid, okay, reacted with sodium carbonate. So therefore, if we have 3.13 times 10 to the power of negative 3 mole of hydrochloric acid, so this quantity of mole of hydrochloric acid should react with, okay, so you calculate this, we are going to get 1.57 times 10 to the power of negative 3 mole of sodium carbonate. Okay, so this is the mole of sodium carbonate reacted. And we knew that, this sodium carbonate, okay, came from the impure sample of sodium carbonate. Okay, so right now we want to determine, okay, what is the percentage, what is the percentage of this sodium carbonate in its impure sample. Okay, right, so since we have already calculated just now the mole of sodium carbonate reacted, and this time we are going to determine what is the mass of sodium carbonate reacted. Okay, so this is the formula. Okay, we are going to use this formula or this equation. So mass of sodium carbonate equals to moles of sodium carbonate times molar mass of sodium carbonate. So mole of sodium carbonate 1.57 times 10 to the power negative 3 mole, so times with 106.01 grams per mole, which is the molar mass of sodium carbonate, and we are going to get 0.166 grams of sodium carbonate. Right, guys, so this is the mass of sodium carbonate. Okay, in order to determine the purity of sodium carbonate, so what we are going to do is mass of sodium carbonate divide by the mass of impure sample of sodium carbonate, okay, and we are going to multiply with 100. Okay, since the mass of sodium carbonate is 0.166 grams and the mass of the sample is 0.2233 grams, okay, times 100, right, so we are going to get how many percent, guys? We are going to get 71.2% sodium carbonate. So this is the purity of sodium carbonate in the impure sample. So means that, okay, so out of 100% of the sample, only 71.2% is sodium carbonate, while the rest, or around 28.8%, okay, so that is the percentage of impurities.
Right, guys, actually this question is the same question in your tutorial 1.3. Okay, tutorial 1.3, question number 2. Okay, question number 2. Okay, so you can look for this question in your tutorial book. Okay, right, so what do we have here? At this time we have an impure sample of zinc weighing 50 grams, okay, reacts with excess hydrochloric acid to produce 18 liters of hydrogen gas at room condition. Okay, and the question here is, firstly, write a balanced equation for the reaction, okay, and then calculate the mole of hydrogen gas produced And lastly, determine the percentage of zinc in the impure sample.
So let's start with the first part of this question, A. Okay, so in A, what we need to do is we are going to balance this equation. So first we have zinc, right? So zinc reacts with hydrochloric acid. We are going to get zinc chloride and hydrogen gas. And remember guys, okay, so this equation is not balanced yet. So what should we do? Come on. Okay, so we are going to start with the most complex substance. Remember in the previous lesson, in the previous videos, okay, we have already discussed on how to balance chemical equation using inspection method. Okay, so we are going to start with the most complex substance. So in this case, zinc chloride is the most complex substance. Okay, so zinc, there is only 1 mole of zinc here, and that's why here also 1 mole of zinc. Okay, but Cl, okay, chlorine, in zinc chloride there are 2 moles of chlorine atoms. So since there are 2 moles of chlorine atoms in zinc chloride, so over here for this HCl we need to multiply, okay, by 2, right? So 2 moles of hydrochloric acid. So now let's check, let's do some inspection on both sides to make sure both sides of this equation is balanced. Okay, so on the left side here we have 1 mole of zinc, on the right side 1 mole of zinc. So we have 2 moles of chlorine, 2 moles of chlorine, and 2 moles of hydrogen, 2 moles of hydrogen. Okay, so the equation is balanced. Good job guys, good job. Alright, next, question B. Alright, so in B, we need to determine how many moles of hydrogen gas produced in this reaction. Okay, if you look at the question, stated in the question, so this reaction, okay, was done at room temperature. Okay, room temperature. So now we know that at room temperature, okay guys, at room temperature, if we have 1 mole of any gas, name it, any gas, if it is 1 mole, okay, so this 1 mole of gas occupies 24 liters. Okay, so don't confuse with at STP. Okay, so at STP, 1 mole of gas occupies 22.4 liters. Those are the for STP condition at STP. But in this question, this reaction occurred at room temperature. So that's why we are going to use this relationship here. Okay, 24 liters of hydrogen gas, okay, occupied by 1 mole of hydrogen gas. So therefore, if we have only 18 liters of hydrogen gas, so this means, okay, 18 liters of hydrogen gas occupied by, so this is how we calculate. Okay, so 18 liters of hydrogen gas times 1 mole of hydrogen gas divided by 24 liters of hydrogen gas. So liters of hydrogen gas cancel. So we are going to get 0.75 moles of hydrogen gas. Okay, so this is the mole of hydrogen gas produced in the reaction or released in the reaction. Right. Next, question C. Okay, in question C, we are going to use the balance equation from question A just now. Right, so from the balance equation, okay, so we knew that 1 mole of hydrogen gas produced from 1 mole of zinc. Okay, so this is a stoichiometrical relationship between hydrogen gas and zinc, right? However, in this reaction, Okay, so the mole of hydrogen gas produced was 0.75 mole of hydrogen gas. So therefore, if the reaction produce 0.75 moles of hydrogen gas, so means that this 0.75 moles of hydrogen gas, okay, was produced from 0.75 mole of zinc. Okay, why? Because the ratio is 1 to 1. Okay, so we have equal number of moles, which is 0.75. Okay, so once we have calculated this, right? Okay, so we want to determine the mass, the mass of zinc reacted with this hydrochloric acid. Okay, so this is the molar mass of zinc, 65.4 grams per mole. Okay, by using this molar mass of zinc, okay, we know that from this molar mass of zinc, 1 mole of zinc weighs 65.4 grams. Okay, that if we have 1 mole of zinc. In this case, or in this reaction, we have how many moles? 0.75 mole of zinc. So therefore, 0.75 mole of zinc should weigh how many grams? Okay, so if we calculate this, we are going to get 49.05 grams, because this is less than 1 mole. See, if it is 1 mole, 65.4, but we have only 0.75, so that's why the mass is less than 65.4. It should be less than 65.4. Okay guys, so this is the mass, the mass of zinc reacted in the reaction. Okay, since we want to determine the purity of zinc in the sample, right? So this is just this is the mass of pure zinc in the impure sample of zinc. Okay, we have just calculated just now, right? And given in the question, right, the mass of impure sample of zinc is 50 grams. So therefore, if we want to determine the percentage of zinc in the impure sample of zinc, right, so how to calculate this? Okay, so mass of pure zinc divided by mass of impure sample, and we are going to times it with 100%. Okay, and substitute these two values into this equation. Okay, 49.05 grams over 50 grams times 100%, and finally we are going to get
98.1%.
So this is the percentage of zinc, or we can say this is the purity of zinc in the impure sample of zinc. So means that the remaining 1.9% is the impurities. Yes, or the percentage of impurities.
Alright, we have come to the last and final question of the day. Okay, exercise 3. And actually, this question actually is the same question as question number 3 in your tutorial 1.3. Okay, so you guys can check in your tutorial book. Okay, it is the same question. Alright, so I'm not going to read this whole question. So let's convert this question, okay, from here to here. Okay, right, so what do we have in this question? We have a sample of iron ore. Okay, and the mass of this iron ore is 1.55 grams. Right, so for information, guys, iron ore actually contains iron, not just iron, iron and impurities. Okay, impurities. So that's why if we want to extract this iron from this sample of iron ore, so this iron ore must be dissolved in an acid solution. Okay, so we are going to dissolve this iron ore into an acid solution. And what happened to this iron ore? So iron in the iron ore sample will be dissolved in this acid solution to produce iron 2 plus ion. Okay, or iron 2 ion. Okay, clear everybody? Right. And then in the next part of this question, okay, stated in the question. So this iron 2 solution later on is titrated, with potassium or with 0.02 molar potassium permanganate solution, KMnO4. Okay, and what happened in this titration? Okay, permanganate ion from the potassium permanganate is reduced to manganese 2 ion. Or we can say that this permanganate ion undergoes reduction. Okay, while iron 2, iron 2 ion from the acid solution here, okay, is oxidized to form iron 3. Or we can simply say that iron 2 undergoes oxidation. And both of these reduction and oxidation occurred simultaneously. And that is why this reaction or this titration is also known as redox titration. Okay, redox titration. Right, and then in the last statement in this question tells us, okay, this titration requires 92.95 milliliters of potassium permanganate to reach equivalence point. Okay, what is equivalence point? Sounds familiar, right? Equivalence point. I know you have heard it somewhere before. Okay, so what is equivalence point? So equivalence point means the point in a titration at which the added titrant, what is the titrant here? Yes, the titrant is potassium permanganate, reacts completely with the analyte. So in this case, the analyte is iron 2 ion according to the stoichiometry. Okay, or in other words, we can say that equivalence point is the point at which both reactants reacted completely according to the stoichiometry. Okay, so it means that all of the reactants completely reacted. Right, so that is what we call as equivalence point. Equivalence point. Okay, and since this is a redox reaction, so that's why in the first part of this question A, we need to write down the balanced redox equation for this reaction. And in B, what we need to do is we need to determine, okay, what is the percentage of iron in this sample of iron ore.
Right. So let's start with the first part of this question. We need to write a balance equation for the titration. And since this reaction is a redox reaction, so we are going to do balancing redox equation using ion electron method. Remember in the last video, in the last lesson, okay, we have already discussed about this, right? Okay, so how to balance redox equation? So we were given the two half equation. The first half equation is permanganate, okay, is reduced to manganese 2, okay, reduction, and iron 2 is oxidized to iron 3. Okay, remember once we have separate this redox equation into two half equations, right, and the next step is we are going to balance the number of atoms other than oxygen and hydrogen. So in the first half equation, reduction equation here, reaction here, okay, so on the left side there is 1 mole of manganese, the right side 1 mole of manganese, so the number of atoms of manganese on both sides, okay, are balanced, so no need to do anything, right? And then let's look at iron. So on the left side 1 mole of iron, on the right side also 1 mole of iron, so therefore the number of mole of iron atoms also balance on both sides, so no need to do anything. Okay, next we are going to balance atom oxygen, and also we are going to balance hydrogen atoms. Okay, so in this case in permanganate there are 4 moles of oxygen atoms here. Okay, 4 moles of oxygen atoms, so means that on the right side here we need to add 4 moles of water. And once we have added 4 moles of water, we have increased the number of mole of hydrogen from 0 to 8 moles of hydrogen. So we need to balance this 8 moles of hydrogen atoms by adding 8 moles of hydrogen ion on the left side. Okay, right. So in terms of atoms, okay, we are done, okay, for the first half equation. And then let's move to the second half equation. So for second half equation, or for this equation that involve these ions, or since there are no atoms other than iron, okay, so that's it, okay? No need to do anything, right? And then we are going to balance the charges, okay, the charges. Okay, so for the first half equation, since we have 8 moles of H plus, means plus 8 the charge, and permanganate is minus 1, right? And manganese 2, okay, is plus 2, and water is 0. Okay, so if we total up the charges on the left side, we are going to get plus 7, while on the right side we are going to have plus 2. So it means that the charges are not balanced on both sides. Okay, so we need to add electrons. So how many electrons must be added, and which side should we add this electron? Yes, we are going to add electrons on the left side. So how many moles of electrons need to be added? Okay, good. So we need to add 5 moles of electrons. Okay, why 5 moles of electron? Because 5 mole of electrons carry negative 5. The charge is negative 5. So therefore, negative 5 plus 8 plus minus 1. So we are going to get no longer plus 7. It should be plus 2. See? On the left side is plus 2. On the right side also plus 2. So it means that the charges on both sides of this first half equation is balanced. Alright, good. Okay, so let's move on to the second half equation. Right, so on the left side of this equation, okay, the charge is plus 2, and then on the right side also plus 3. Okay, so how to balance these different charges here? Okay, we are going to add electron on which side? Yes, on the right side. Okay, we are going to add 1 mole of electron. Okay, so since 1 mole carries negative 1 the charge, and the total charge on the right side would be plus 2. So therefore the charges on both sides are balanced. Okay, are balanced. Okay, so once we are done with balancing the charges, we are going to combine these two half equations to form the final equation, or to form the full redox equation. But the problem here is the number of electrons on both sides of both equations, okay, are different. Because if we want to combine these two half equations together, okay, the number of electrons on both half equations must be equalized. Why? Because these electrons must be cancelled at the end. Okay, because at the end we are going to cancel these electrons, so that's why, okay, the number of electrons must be equalized on in both half equations. So what should we do, guys? Yes, okay, so the second half equation here, so to equalize this number of electrons, since in the first half equation there are 5 moles of electrons, so that's why in the second half equation also we need to change this 1 electron into 5 moles of electron. And since we have multiply, okay, with 5, so the whole equation also must be, okay, times 5. Okay, so the half equation, the second half equation, okay, will look like this. Okay, right, and then we are going to combine these two half equations, right? So these 5 moles of electron cancel, 5 moles of electron cancel, and we are going to add up these two half equations, and finally this is our balance redox equation, right? Is this reaction in acidic or basic medium? How can we tell? Actually this is in acidic medium or acidic solution. Remember in the question, at the beginning of the question stated there, this sample of iron ore is dissolved in acidic solution. See, acidic solution, and that's why this reaction actually occurred in acidic medium. So we are going to stop here, so no need to add the last step. So this is the balance redox equation for this redox titration. For question B, we need to calculate the percentage of iron in the sample of iron ore. Right, so in the question, given in the question, at equivalence point, potassium permanganate and iron 2 ion from the acid solution, reacted, completely reacted. But at this moment, we do not know yet how many moles actually of potassium permanganate reacted with this iron 2 ion. So that is what we are going to determine first. We are going to determine how many moles of potassium permanganate actually reacted at equivalence point. So at equivalence point, mole of potassium permanganate reacted is equals to molarity of potassium permanganate solution times volume of potassium permanganate. So volume here means volume of potassium permanganate needed to reach equivalence point. So if we substitute the values, so 0.02 molar times 0.09295 liters, right? So we are going to get 0.001859 moles. So this is the mole of potassium permanganate reacted. And we know that in the redox reaction, permanganate ion from the potassium permanganate undergo reduction to produce manganese 2 plus. So since 1 mole of potassium permanganate contains 1 mole of permanganate, so therefore if we have 0.001859 moles of potassium permanganate, it contains 0.001859 moles of permanganate. And from the balance equation, 1 mole of permanganate reacts with 5 moles of iron 2 ion. So therefore, if we have 0.001859 mole of permanganate, it should react with 0.009295 mole of iron 2. And remember, this iron 2 ion actually came from iron in the iron ore. Remember iron ore, when we dissolve iron ore into the solution of acid or into this acid solution, so this iron in the iron ore dissolve to form iron 2. Remember? So that's why the moles of iron in iron ore and the moles of iron 2 in the solution, actually both of these, same mole, same number of mole, which is 0.009295 mole. Alright. Okay. The mass of iron in iron ore is equals to moles of iron in iron ore times molar mass of iron. So if we solve for this, 0.009295 mole of iron in iron ore times its molar mass of iron, and we are going to get 0.5191 grams of iron in the iron ore. And then finally, okay, so we want to determine the percentage of iron in the 1.55 gram sample of iron ore, right? So mass of iron in iron ore divided by mass of iron ore times 100%. Okay, you substitute the values. Okay, 0.5191 grams divided by 1.55 grams times 100%, and finally we are going to get 33.49%. So this is the percentage of iron in the sample of iron ore. Right, that's all for now. Thank you for your time, okay, for watching this video. And in the next lesson, in part 3 of this lesson, we are going to discuss another two terms. Okay, another two terms. The first term is we are going to have a look at the limiting and the excess reactant. Okay, and lastly, we are going to discuss on percentage yield. Okay, percentage yield. Right, guys. Okay, so thank you once again. Bye bye.